Hello everyone. In my previous video, I have given the definition of MGF and I have shown how to find MGF of binomial distribution and Poisson distribution. Now we will see how to find MGF of normal distribution. Since normal distribution is a continuous probability distribution, probability function of the normal distribution is 1 upon sigma into square root of 2 pi e to the power of minus half into x minus mu by sigma whole square, where mu is a mean and sigma square is a variance. So the moment genetic function of the normal distribution is mx of t equals to integration of e power tx into f of x dx, where f of x is a probability function of the normal distribution. To further simplify this, we have to take a substitution for x minus mu by sigma as a z. This implies x equals to sigma z plus mu. On differentiating this both the side, we get dx equals to sigma dz. So that mx of t will be integration of e power t into sigma z plus mu upon sigma square root of 2 pi e raised to minus half z square sigma dz. Now the sigma gets cancelled and the limit will remain same, minus infinity to infinity. We can take all constant outside the integral. E power t mu and root 2 pi will keep outside the integral. Integration of e power t sigma z minus half z square dz, where z takes the value from minus infinity to infinity. Further, we'll take this minus half outside. So we get minus half into z square minus 2t sigma z. To simplify this further, or to complete the square, we have to do small adjustment, that is by adding sigma square t square and subtracting sigma square t square. So we'll take this minus sigma square t square outside the bracket. E power minus half into minus sigma square t square will be e power sigma square t square upon 2. Since it is a constant, we'll take it outside. What remains is z square minus 2t sigma z plus sigma square t square. So that is nothing but z minus sigma t whole square. So further, we'll take z minus sigma t as a y. This implies dz will be dy. So mx of t will become integration of e power minus y square by 2 dy. So since this function is even function, we can write integration of the function from minus infinity to infinity as a 2 times of integration of the even function from 0 to infinity. So 2 by root 2 pi will become square root of 2 by pi. And using gamma function, integration of e power minus y square by 2 dy from 0 to infinity will be root pi by 2. So this root 2 by pi into root pi by 2 gets cancelled. We get e power t mu plus sigma square t square by 2. So this is a moment generating function of normal distribution. You can try to find expectation and variance for the normal distribution using MGF by finding mx dash of 0 and mx double dash of 0. Now I will solve some problems on moment generating function. If x is the outcome obtained when a die is tossed, then find the MGF and also find its mean and variance. So here x is a discrete random variable where x takes the values 1, 2, 3, 4, 5, 6, and probability of each outcome when die is thrown is a 1 by 6. Moment genetic function is expectation of e power tx. Mx of t is the expectation of e power tx. That is the summation of e power tx into p of x dx, where x takes the value from 1 to 6. That is e power t probability of x1 plus e power 2t probability of x2, so on, e power 6t probability of x3, and the probability of each x is 1 by 6. So we get 1 by 6 into e power t plus e power 2t, so on up to e power 6t. So this is a moment generating function of the given random variable. So next, to find expectation or a mean of the random variable, we have to find out mx dash of t. That is the differentiation of mx of t. So that is 1 by 6 into e power t plus 2 into e power t 2t, so on up to 6 into e power 6t. Then put t equal to 0, we get mx dash of 0 as e power 0 plus e power 0, e power 0 plus 2 into e power 0, so on up to 6 into e power 0 divided by 6. That is 1 plus 2 plus 3, so on up to 6 divided by 6. We get 21 by 6. So this is a expectation or a mean of the random variable. Similarly, we have to find the variance. To find the variance, first we need to find mx double dash of t. That is the differentiation of mx dash of t with respect to t. E power t plus 4 into e power 2t, so on up to 36 e power 6t whole divided by 6. Then put t equal to 0, we get 1 plus 4, so on up to 36 divided by 6. That is 91 by 6. This is nothing but expectation of x square. So we know the variance of x is e of x square minus e of x whole square. That is 91 by 6 minus 21 by 6 whole square. We'll get it as 2.91. Next problem. If x is a random variable having the values 0, 1, 2, so on, and p of x is a, b power x, where a and b are positive numbers, and a plus b equals to 1. Find mgf of the random variable x, and if expectation of x is m1 and expectation of x square is m2, show that m2 equals to m1 into 2m1 plus 1. So here the random variable x is a discrete, it is clear from the question. So mx of t is summation of e power tx p of x, where x takes the value from 0 to infinity, summation of e power tx, where p of x is given as a into b power x, where x takes the value from 0 to infinity. Expand this by taking constant outside. So we get 1 plus e power t into b plus e power t square into b square, so on. So now this is geometric progression with first term a equals to 1 and common ratio r equals to b into e power t. The sum to infinite terms of geometric progression is 1 upon 1 minus r, where r is b into e power t. So the moment generating function of the given random variable is a upon 1 minus b into e power t. Further, it is given that a plus b equals to 1. So we can write a as 1 minus b upon 1 minus b into e power t. So next let us find expectation of x, that is mx dash of 0. For that we have to differentiate mx of t with respect to t once. using quotient rule. We get 1 minus b into e power t whole square. In the numerator, it will be b into e power t into 1 minus b. Then putting t equal to 0, we get mx dash of 0 as b into 1 minus b upon 1 minus b whole square. 1 minus b gets cancelled. So we get b upon 1 minus b. This is expectation of x, and it is given that expectation of x is m1. So b upon 1 minus b is m1. So I'll take this as a equation 1. Further, we'll differentiate mx dash of t with respect to t. That is mx double dash of t. We get 1 minus b into e power t whole square, e power t b 1 minus b plus whole divided by 1 minus b into e power t to the power of 4. Then put t equal to 0. We get b into 1 plus b divided by 1 minus b power 4. So this is expectation of x square, and it is given that expectation of x square is denoted by m2 in the question. So we'll take the right hand side of the required thing, that is m1 into 2m1 plus 1 and m1 is b upon 1 minus b into 2 into b upon 1 minus b plus 1. On simplifying this, we get p into 1 plus b upon 1 minus b whole square. So this is nothing but m2. So here it is 1 minus b whole square on applying t, substituting t equal to 0 and mx double dash of t. So we get the required thing, m1 into 2m1 plus 1 is m2.